In this video, we shall learn about a well-known theorem which starts with some random sample x1 to xn from normal mu sigma square, where mu is an ideal number and sigma square is strictly positive. We define the sample mean as usual, x bar, and the sample variance as 1 over n, this quantity. Now some of you may be used to thinking of this as 1 over n minus 1. That will hardly change the main statement of the theorem. Then there are three different implications. Number one, x bar has normal mu comma sigma square by n distribution. Number two, n squared by sigma square has chi-square distribution with degrees of freedom n minus 1. So in case you are used to n minus 1 here, just make it n minus 1. So my main statement is this thing divided by sigma square has chi-square n minus 1 distribution. And number 3, x bar and a square are independent. Now, before starting to prove this theorem or even discuss this theorem, let me first observe that without loss of generality, I can take mu to be equal to 0 and sigma square equal to 1. And this is the reason. Suppose I define yi as the standardized version of xi, subtract the mean, divide by standard deviation, which I can do because sigma square is positive. In that case, just imagine that you have proved the theorem for yi's. So yi's, you can see, has normal 0, 1 distribution. Now when you do this, you will observe that you will have corresponding y bar, and this y bar will be nothing but x bar minus mu by sigma. And similarly, a square, which I will now call sy square, computed based on yi's, will be just a square by sigma square, because the subtraction of mu will have no effect, but you have divided this by sigma, that comes out as sigma square, so it will be this. So if you are able to prove the theorem for the yi's, in that case you can always get back to your xi's. So without loss of generality, I can assume that this is 0 and this is 1. So this also becomes 0 and this is 1, and similarly I do not need this denominator at all. So it is in this incarnation that we shall prove it. Now there are various ways of proving this theorem, but we shall prove it in a way that is easy to be generalized, because this theorem is actually the simplest in a line of theorems. So we want to give a proof which will also generalize to all the other theorems in the class. So let's first discuss why it belongs to a class of theorems. Suppose someone gives you a random sample. Why on earth would you ever care about computing x bar? The main idea is that these are all random quantities, they come from the same distribution, and we often like to think of random quantities as being measurements. So there is some true value of the measurement, and the reason why they are slightly different from each other is because there is some amount of random error. So you believe that there is something called the true length. So ideally all these things should have been the same number. Now we want to know which number would be the best representative of all these things, and the answer to that is x bar. So if you want to represent all these things by the same number, and in the process you want to do the least amount of error, then you will choose x bar. Now let's think of it in terms of some linear algebra. I said that all these things should be the same number. So they should be all like A. So ideally it should have been a vector, like all the numbers are the same, and all such vectors constitute span of the vector 1. Vector 1 means the vector which consists of 1 in all its entries. So we expect ideally that all these numbers should be the same, have there been no measurement error. So we expect that this should be in the span of this particular vector. But unfortunately, it is not in the span of this because there are some random measurement errors. So this is my origin R in Rn, and this is suppose this vector. I expected that my random sample would be a vector along this line, but unfortunately it isn't. So it is something like this. This is my x vector consisting of the components x1 to xn. But naturally, we would expect that it should be pretty close to that because after all, I am measuring the same quantity. So, what is the best way of representing this vector by something along this direction? To take the closest vector naturally. Now, if you take the closest vector, you can convince yourself that this vector will have entries x bar x bar. Because anything along this must have all components equal, and this will be the best possible approximation in the sense this will be the perpendicular. Now, of course, this vector is not exactly same as this vector because of all those random errors. So this is the amount of error that you are committing when you are using this as an approximation for that. And what is the length of this? The squared length, you will notice, is precisely this quantity. From this, you subtract this and then you take its norm square. For each component will be like xi minus x bar, square them and add, and that will be the norm squared. So this measures how far your actual observed vector is from your ideal vector. Once you look at it in this way, now it should be quite easy why the theorem is true, because we are basically doing the following. We are taking our x vector, projecting it orthogonally onto the span of 1 as well as onto its orthogonal complement. These are the two components. Now we immediately know that this and this being orthogonal, their projections are also going to be independent. That's something that we have already discussed in one of the earlier videos. Number one. Number two, what is this thing? This is orthogonal projection of a vector, all whose entries are IID normal 0, 1 onto a space of dimension n minus 1. Because this has dimension 1, the total thing has dimension n, so it has n minus 1. So immediately you see that this must have chi-square with degrees of freedom n minus 1. And this one is directly straightforward because this is already a linear combination of xi's and they are IID normal 0, 1. So when you want to find out the mean, you take the same linear combination of the means, that will still give you 0. And for variances, you just add up the variances of this thing, that being independent, you will get n. When you divide by n, the variance gets divided by n squared, so you get 1 over n. So that's how you get that theorem. So think of the theorem in this orthogonal projection way. Now why is it one of a class of theorems? Because here we did a simple statistical model. And the model say, whatever your actual observation is, I believe that it should be along this line. That is what is called the model space. So the model space in this case has dimension 1 and you projected it orthogonally to get this vector, which is the best possible approximation that your model provides to reality, and this gave you a measurement how far off the truth is from your model, or the actual observation is from your model. Now if you try to come up with a more complicated model, this model space need not be just one dimensional, it could be some p-dimensional, then also you will have a very similar theorem. This will have norm square given by chi-square n minus p. And there is a whole class of statistical models where the model space is a subspace in the linear algebraic sense, and you can apply this same argument. Suppose I have two vectors u and v, and I want to find out the component of v along u. In our language, it is the orthogonal projection of v onto the span of u. Obviously, it should be a multiple of u, and that multiple is given by u transpose v, that is the dot product between u and v, divided by u transpose u, norm square of u, that's a scalar, times u. Now that is something you possibly already know. If I think of this as theta, you can think of it as cos theta, etc., and you will get that. Using this result, you have to justify one step of our proof. I had our observation vector x and that 1, 1 vector, and I want you to find out this particular vector. I have already mentioned that it should be x bar, etc. up to x bar, but I want you to prove this using this formula where the role of v is played by x and the role of u is played by 1. Just apply this formula and see whether you come with this.